today we start with the nature or the essence of space.
Space.
What is space? Because it has to be more than just distance.
Well, space is the final frontier. That's what I learned as a child. It's where we want to go, right? It's what activates our imagination and gets all of the creativity flowing. But if you ask a philosopher, they get a lot more abstract and they go like, oh, well, space, it's like the three-dimensional extent where objects live, which to me that means nothing, right? But then what's an extent and why do objects live there? And is space there when we're not, putting objects in it? Like, do you need air and water for there to be space? So it gets really deep and philosophical and confusing. So physicists don't like that, as you can imagine. So to a physicist, space is the distance, if you want, that an object travels in a given amount of time at a given velocity. That's it.
Really?
Yeah. Space is what a ruler measures. I told you time was what a clock measures.
Right. Space
is what a ruler measures.
So it is just distance.
If you want, yeah.
Right, because you don't need air, or you don't need water, you don't need an object to have space.
Yeah, so if you think of it operationally, yeah, space is the thing where objects live, but what we care about is the relationships in space between different objects. And the relationships in space are defined by a ruler. And then you can ask, well, what's a ruler? Okay, so, it's... In fact, did you know that the word ruler is perhaps misused in the English language?
I did not know that.
Yeah, it turned out that a ruler is supposed to be an instrument used to rule straight lines, like to draw straight lines, not an object to measure distances. An object that measures distances should be called a measure. And the only word that we have that still is used like that today in the English language that I could figure out or find out was the tape measure. Because that's, the device is used to measure distances, but, if you ever try to draw a straight line with a tape measure, it's sort of tough.
Yes, it is. it very much is, especially if you get into one of those 50-yard tape measures that are made of nylon. But so, you use a ruler to draw a straight line, but space can be bent.
Space can be bent, but we didn't know that until sort of recently. So there was this idea that space was absolute, that space could not change no matter what was in space and, what was going on around space. Space was space, that's it. The distance between two objects would stay constant no matter what was happening nearby. Of course, assuming that the two objects stayed at their same relative positions. But then this guy called Leibniz, not Einstein, said, maybe space is really a collection of relations between objects. Maybe space is relative. Maybe the distance between objects is relative and not absolute. Maybe the distance can change. And Einstein came about when he was trying to unify gravity with the other forces of nature and realized that the only way to do that was to argue that space could bend, that gravity could contract space. So just like time is dilated or stretched out, if you want, close to a very massive object where gravity is very, very strong, space can also be sort of stretched out in a similar fashion when near a strong gravitational object. The geometry of space and time changes. But I think we should leave that discussion about stretching of space-time for another time because it gets pretty...
I agree with that because what I'm starting to hear, and my thought is turning... with our discussion on gravity and our discussion on time and just the beginning of this discussion on space, all three of these properties, properties is the wrong word, all three of these concepts are interrelated.
Yeah.
Time and gravity and space all exist and manifest themselves through each other.
Yeah. So when you ask me, hey, can we talk about gravity? I was like, sure. How much physics do you know? It's like, oh, okay. No problem. We can totally do this. if I don't choke, we'll be able to do this.
Would you like to take a break?
No, I'm good.
Okay.
But I can't really do this unless we first understand what time is, and unless we first understand what space is. So that's what today is about, is understanding space. Like, how do you measure things? Like, what's a meter? You know what a meter is?
Yeah, it's just under 3 feet.
No, a meter is a bar that's in Paris.
Oh.
Did you know that?
Yes, I did know that there is it's a rod.
Yeah, it's a rod. So it turned out that a long time, actually, meter comes from the word metrio or metron from Greek, because pretty much everything comes from the Greeks. And it means to measure, right? Or a measure. And we had to, as a, civilization, decide on some distance standards. Standards are very important. And, somebody in there with great imagination decided that a meter would be 1/1,000,000th the distance between the equator and the North Pole, because that's a really useful measure. This was in the 1700s, right? And then in the 1800s, like, oh, no, let's have a convention, because we love conferences and congresses like this. So let's have a conference where we define what a meter is. And then the International Bureau of Measures and Weights decided, what we're going to do is we're going to build a bar. And the bar is going to be made of platinum and other elements. And we're going to keep it in Paris. And it's going to be exactly a meter long, with a meter defined in terms of this like distance between the equator and the North Pole. And they, guessed or calculated this the best they could, and then built this bar. And then the bar was off by 200 microns. And then everybody was using a wrong meter for like a while. And people would go and like build other meter sticks out of this meter bar in Paris, so that they could all, machine things to the right precision and so on. But it turned out that the meter was wrong. And now the definition has evolved. Of course, we're still not using this metal bar in Paris. Now we use more sophisticated methods that, involve the speed of light, involve the definition of the second that we talked about before, and so on. So, for example, today, a meter is not defined by a bar. A meter is defined by the distance traveled by light in a small fraction of a second, in 1/299,792 458 parts of a second.
I find it amazing. No, absolutely. But with it's the cesium that measures time.
Cesium-133 is one of the atomic clocks. Yeah.
Right. Well, you're dealing with very, very, very small things.
Yeah.
That in this case, you're dealing with a very, very small distance that light travels in this very, very small period of time. Yet these small numbers are used to extrapolate into ginormous distances.
Yeah, so how do you measure small things and large things? That's tough, right? Because I can take my meter bar from Paris and subdivide it into 100 equal parts, because I'm really good at marking, tick marks, creating tick marks in my bar. I don't think they would allow me to do that.
No, I don't think they would let you do that either.
But anyway, you can do that, and then you can define each tick mark to be a centimeter. That's what a centimeter is. I know we're using metric. Oh my God, my head's going to explode.
Yeah, but everybody understands a 2-liter bottle of Coke.
Exactly.
But another use of the metric system that has been adopted, and I think quite successfully. But going back to that, why would you want to mark a meter bar down to centimeters?
Because eventually you want to be able to measure things that are a lot smaller than a centimeter. Okay, so eventually you want to build microchips that have to be sitting right next to other electronics that are really tiny. And you need to know how small your electronics should be if they have to sit right next to something else in a motherboard or inside of a computer, right? That's, a motherboard is one of the principal components of a computer. And it has all sorts of different chips, microchips. And these have been machined to exactly the right precision. This, we're talking about really small distances. And if we don't know what a nanometer is or a micron is, then and if we don't agree on this, on how we define a micron or a nanometer, then how are we going to go and build chips that, I can then ship, I can build it here and then ship it to New York so that it can be assembled? if we haven't agreed on what a nanometer is. So then we start subdividing things, and we subdivide it and subdivide it and subdivide it until we can't do it anymore because, my pencil is thicker than the distance I'm trying to measure. So then what we do? What do you think we do? Like as physicists, this is lovely.
Well, first off, it's 1450 KMMS, 1340 KPRK, and I just bought myself a couple more seconds to try to formulate an answer, but I don't know what we do.
Oh, come on. What you do is you shoot the thing with something, and you try to collect what comes out, on the other side, right? You shoot your sample with electrons.
Okay.
And then you measure the electrons on the other side, and it sort of defines an electron microscope.
So what you are telling me is the understanding of space is responsible for electron microscopes as well as computers.
Well, the need to
standardize
and define things at ever smaller scale so that we can then do experiments, so that we can then build machines, is eventually what leads us to the construction of the microscope, so that we can understand what happens inside of a cell, so that we can understand what happens or how to build things that are smaller, these nanotubes that people talk about, that are smaller than what we can see with our normal eyes, right?
It's 1450 KMMS, 1340 KPRK, MSU physicist Nico Yunes joining me in studio, and we're discussing the nature of space. We started with the very micro, and I guess you want to flip over to the macro.
Yeah. How do we measure long distances? Because it's sort of inconvenient to stack meter sticks from here to the moon to see how far the moon is, right?
Right. Well,
that wouldn't work.
We can just shoot a laser to the moon, have it reflect in time how long it takes to go up and back, and then divide by 2.
Yeah! Let's shoot the moon! And we do this all the time, and it's awesome. This is called lunar laser ranging, okay? And it started like in the 60s, I think. And initially, they would just like shoot the moon. And then, of course, it's just a laser. It's not going to make the moon explode or anything like that. It's high power here on Earth, but by the time the laser gets to the moon, because it loses power as it travels, it's really not that powerful at all. And, you're talking about a beam that on Earth is, maybe, like 1 meter, 2 meters wide or something like that. And then the number of photons you detect when the thing comes back to Earth is like 1 photon every few seconds. So you lose a lot of power as you get to the moon.
So my laser pointer that I can go by.
Never going to get to the moon.
We'll never get to the moon.
There's all sorts of effects in the atmosphere, absorptions and deflections and so on. So initially what they did is they just shot a laser to the moon, and they used the surface of the moon to like reflect the light and collect it back, and they got some measurement of how far away the moon was. But then, and this was like in the early 60s by people at MIT, and then they realized like, wait, we're sending people to the moon because it's the 1960s. Why don't we let them carry a reflector dish and then try to aim our lasers at this reflector beam, and now we'll hit it because we are really good.
Yeah, because we are MIT scientists.
and then the light will reflect from these retroreflectors and then bounce back, come to Earth, we'll detect it, and we'll have a much better measure. And reflecting out of a retroreflector, like they're called, is much more efficient and much more accurate than doing off the surface of the moon, because the moon has lots of mountains and valleys and craters, and so it's not a very nice surface. But a retroreflector, you can make it perfectly smooth or very close to perfectly smooth.
Plus, it is an exact point on the moon that you can use reliably to test.
Yeah, unless you lose the retroreflector, which happened. So so Apollo 11, 14, and 15 put these retroreflectors there. And of course, the Russians, or Soviets to be more precise, also did the same. But one of the retroreflectors the Soviets put on Earth, on the moon, sort of got lost. They didn't know where it was. In the sense that they thought it would be in some part of the moon, and then they were shooting lasers there, and nothing was coming back, effectively. Until very, very recently, in the 2000s, some American scientists
discovered it again?
Discovered the retroreflectors of the Soviets. And then the measurements have become a lot more accurate. And you do this like everywhere now, like it's done in the US, in France, in Russia, in the Apollo telescope, the Apache Point Observatory, which is, I think, in New Mexico. And by counting the amount of time, by measuring the amount of time it takes for this light to leave Earth, hit the moon, come back, and be detected on Earth, and then divide by 2, and using the fact that the speed of light is the speed of light is the speed of light, it doesn't change, then you can calculate the distance to the moon very, very accurately. It's something like 300 or almost 400,000 kilometers on average.
So why is it important to have an understanding of space? And what are the physics that are applied other than building my computer or polishing lenses? What is the practical application of this understanding?
Of understanding
of space, and why should I be excited about the understanding of this part of physics?
Oh, because initially, when you're trying to understand space, as it's usually the case in science or in physics in particular, in basic pure research, you're not going after building the new iPhone. You're going into trying to get a better and deeper understanding of how the universe works. That's what drives us, to try to get an understanding of the inner workings of the universe, a practical understanding, if I may quote a TV series. Now, in order to acquire that understanding, we have to build machines. We have to build instruments that can allow us to make better and better measurements. And when we're talking about space, we're talking about measurements of distances. Okay, so we want to know how far away or what's the size of atoms. We want to know what a nanometer is. We want to be able to probe things inside of cells. Okay, and in order to do things like that, we need to build microscopes. We need to build machines that allow us to do something called interferometry, where you're really measuring. You're using light. Bouncing light off mirrors to measure the distance between say, 2 sets of mirrors. And in fact, that has then translated into a technique to determine how well polished a piece of glass is in the optics industry. By using interferometry and interference in particular, you can determine whether you've polished your piece of glass sufficiently well or whether there are scratches or whether polishing was not sufficiently accurate. And this polishing matters because, then this is used in all sorts of applications like lasers, like cameras, and so on. So if you allow me, it honestly trickles down in the most unexpected way sometimes. Because you see, we are driven to understand the cosmos better. And we are scientists, so we don't live in the cloud. Well, we do live in the clouds, but we base our science on measurements, on building an experiment with which we can take data, and then allowing other scientists to repeat the experiment in an unbiased, as unbiased as possible way, to confirm that what we've measured is correct. That's what science is, what physics is. But in order to do the experiment, sometimes we have to invent technology. And so we have to work with engineers. We have to work with architects. We have to work with all these other people so as to push technology and push the development of new machines so that we can do our experiments. And then once the machine is built, well, look, we have an electron microscope. We can use it for all sorts of really cool things.
It's 1450 KMMS, 1340 KPRK. Nico, this will be my final question for you this morning. Now that we have a basic understanding of gravity and a basic understanding of time and a basic understanding of space, time-space fabric, or the continuum of time-space, would, if any one of these properties, once again I use the word properties, one of these 3 basic concepts, if any one of them were removed, the other 2 would no longer function as the way they do?
Good question. So now that we understand time-ish, and we understand space-ish.
And gravity-ish.
Well, forget about gravity for a second.
Okay.
You might have noticed that space and time have very similar properties. They're defined for physicists in terms of measuring or using an instrument to measure the separation in time or to measure the separation in space. Okay, and as we talked about earlier and last Wednesday, time does not flow at a constant rate. So that means the separation between 2 events in time might be expanded or contracted. And the same thing with the separation between 2 objects in space. It can be expanded and contracted. So what if space and time aren't really all that different? What if they're part of the same continuum? Okay, what if space and time were in more of an equal footing than you perhaps expected? Okay, if that were the case, you could construct a continuum of space and time. And what can you do with that continuum of space and time?
Build warp drives for my starship?
Yeah, we'll talk about that in the future. Which future, we don't know. But in the future, that's what then leads us to the theory of general relativity. It leads us to a much better and much more precise understanding of how nature works, of how gravity works, of how the cosmos came to be, as far as we can measure it.
Well, I said that was going to be your final question, but this led, it's thought on that very chain of thought that led Einstein to his theory of special and general relativity. Two separate theories, by the way. Why hasn't anybody, because that was groundbreaking in the early 1900s with what Einstein did, why has there been such an impediment to future thought of something just as groundbreaking? Or is it that there have been groundbreaking thought that we just don't understand as a general population of people?
Yeah, that's a very interesting question, actually, and it's one that I've thought about before, and I don't know that anybody really has an answer. I think it's a multitude of effects, it's a multitude of circumstances that came about in the early 1900s that allowed Einstein to develop this theory. So first of all, there was a crisis scientifically that people might or might not have been aware of, that, the theory of special relativity was just not compatible. It did not play well with Newtonian gravity, okay? And that had to be resolved. It's not possible to have two theories that don't mesh together. That means that there's a fundamental problem and that we should work hard to overcome it. On top of that, Einstein was pretty smart, and he decided to work on this. On top of that, he had lots of really good friends that were really good at mathematics and really good in physics, and he could talk to them, and they were very welcoming. And on top of that, the scientific community, and I think, academia in some sense, was a lot more less specialized and a lot broader. So people weren't just working on one little corner of a particular area, but rather they were more, perhaps they were less deep in any particular area, but they were much broader in all areas. And if you're trying to resolve an incompatibility between two theories, then it really helps to know a lot about lots of different things, as opposed to, really an immense amount about a single thing. Because if you know an immense amount about a single thing, then it's much more difficult to make connections between these two areas of knowledge. So I think it's a way of learning and a way of teaching and a way of thinking that was developing in the 1900s that had to do with philosophy and it had to do with academia. It was also this crisis scientifically, and it was also the circumstance that you had really brilliant physicists, and we still have really brilliant physicists today. And if you want, we also have a crisis because quantum mechanics and gravity really are incompatible. Mm-hmm. So from that point of view, we're sort of in the same boat as we were in the early 1900s. But two things are different today. Mm-hmm. One is that we've become a lot more specialized. So it's sometimes more difficult for us to see connections between different sub-areas because we're just so concentrated in what we are doing. That's one problem. That we're slowly overcoming, but that's a problem. The internet and being able to be in constant contact with everyone helps. But I think the other problem, and that this is a practical problem, but it's one that I don't see how we are going to be able to get around in the near future, is that we've gotten to the level where, in order to make progress, so every time you have a crisis like this, it helps a lot to get hints from nature as to which way to go. And how do you get hints from nature? You go and measure things that happen in nature. You build a new instrument and you measure something, okay? Mm-hmm. Quantum mechanics and gravity are incompatible when you're dealing with phenomena that are very, very, very micro and very, very, very gravitationally strong. Mm-hmm. And unfortunately, that just doesn't happen on Earth, and it doesn't happen simultaneously on Earth. That doesn't happen simultaneously in the solar system. You really need to go like to a black hole. And black holes are pretty far away from us. I mean, we can't even get to Mars. So it's very, very difficult to go and get hints from nature about what's happening near a black hole or inside of, well, you would never be able to really get information out of a black hole, in spite of what Interstellar may tell you. So there's a practical difficulty here. How do we move forward when we have so limited data to move forward? So few hints from nature as to which way to go. If we can come up with 10,000 different hypotheses, but if we can't go test them to determine which ones are right and which ones are wrong, then the job is a lot more difficult.
So you heard it here. Physicist Nico Yunes, based on his advice, and correct me if I misheard you, liberal art majors, befriend a physicist major and help them expand their horizons.
Yes, please. We need your help.
Nico Yunes, as always, I thoroughly enjoy these conversations and I appreciate your time. Thank you for once again returning, and I'll see you next week.
Absolutely. Thank you so much, Chris.